Welcome to the first in the geometry and topology seminar at Durham. So it's a pleasure to welcome Jason DeVito from the University of Tennessee at Martin, and he's going to talk about double disk bundles. Thanks.
Thank you, Fernando, and thank you for the invite to the seminar. So I guess we'll go ahead and just dive on in. First thing I should say is that a lot of the ideas in this are joint work with, Fernando Galaz-García and Martin Kerin. The main theorem I want to talk about is, it's actually in its own paper, but it's a lot of the core ideas started off with another paper that Fernando and Martin and I were writing. So I guess we'll go ahead and dive on in. I mean, you can read the bar on the left that's going to give the outline, but just to kind of get up on the screen, there are 5 main ideas I'd like to talk about. I want to start with some motivation. What are the geometric problems that I care about? Where do they fit into the bigger scheme of things? I would like to talk about some definitions and examples of, so what is a double disk bundle? Where do these things arise, both by construction and then also by just you're studying a geometry problem and one of these things jumps out at you. And then I want to specifically focus on a conjectural case where double disk bundles arise, and this is the so-called double soul conjecture. And if nothing else, I hope you take this talk as a motivation or an advertisement for studying the double soul conjecture, and maybe hopefully someday someone can prove it. And then I want to mention some results. So the results I'm going to talk about are topological in nature, but they have geometric corollaries if the double soul conjecture is proven. But the results I'm talking about are not contingent on the double soul conjecture, but their applications to geometric problems are. And then the last thing I want to hit here is proof ideas. So I'll go through one of my most recent theorems in this subject, and then we'll talk about how one might prove such a thing. Okay, so diving into motivation. Kind of the big question that I care about is which manifolds admit a complete Riemannian metric of non-negative sectional curvature. I should mention that I'll very quickly stop saying sectional curvature, but for purposes of this talk, I exclusively care about sectional curvature. So we're asking about non-negatively curved Riemannian manifolds, and there are some very important structure results. So I want to start off with kind of the non-compact case. In the non-compact case, we have an amazing theorem due to Cheeger and Gromall. It's called their Soul theorem. And what it asserts is that in the non-compact case, if you have a complete Riemannian manifold with a non-negative sectional curvature, then in fact there's this special submanifold called a soul. That special submanifold is closed. It's a compact, no boundary. It's totally geodesic. In fact, it's better than that. It's totally convex, meaning that if you have a geodesic in the big manifold that starts and ends in the soul, then it was actually contained in the soul for all time. And topologically, your manifold is given as it's diffeomorphic to the normal bundle of the soul. So in particular, the manifold deformation retracts to this closed submanifold, and so somehow that submanifold contains all the topology of this non-compact example. So in a lot of ways, this reduces the problem of classifying manifolds that admit these kinds of metrics to the closed case. Now, I should mention there's a very important, very open question still about this, and that is if I hand you a closed manifold that has one of these kinds of metrics on it and ask about what vector bundles over that have metrics of non-negative sectional curvature, it's still pretty wide open in a lot of cases. So for example, over the 2 torus, there are known examples of vector bundles which do not admit metrics of non-negative sectional curvature. This is a result of Walshop and Ozeiden. But then over spheres in low dimensions, S2, S3, S4, S5, and S7, the result is that all vector bundles over them admit metrics of non-negative sectional curvature. And then there's some partial results for other spaces such as CP2, et cetera, et cetera. And there's several stable results about up to stable equivalence. Every vector bundle admits one of these kinds of metrics or things like that. But generally speaking, if I hand you a closed manifold and say, tell me about the vector bundles over it that admit a metric like this, that's a wide open problem. And that's a very important missing step to saying that we've reduced out of the closed case. Nonetheless, for purposes of this talk, I want to focus on the closed case. So I want to focus the question down to closed manifolds, and I want to go ahead and list some obstructions that are known. Just go ahead and get several up on the screen. So excuse me, one of the most well-known obstructions to admitting a metric of non-negative sectional curvature is Gromov's Betti number theorem. So what this theorem asserts is in each fixed dimension, there's a constant with the property that if you have a manifold that has one of these nice metrics, and you sum the Betti numbers of that manifold with respect to any field coefficients, that total sum is smaller than this constant that Gromov gives. And the constant he gives is explicit, but it's not a very sharp bound as far as we can tell. So it's something like doubly exponential. And then there's some other conjectures I'll talk about later, which imply that the bound should just be exponential. But nonetheless, you still have this constrained topology for any non-negatively curved closed Riemannian manifold. You also have the A hat genus, which is actually an obstruction to positive scalar curvature. And in the context of simply connected manifolds, which is what I'm going to turn focus to eventually, the non-existence of a positive scalar curvature metric will also rule out a non-negatively sectionally curved metric. And so there's that result. And then the last one I'd like to mention is a result of Wilking that is that the fundamental group of the manifold is virtually abelian, meaning that it has a finite index subgroup, which is abelian. So there are several obstructions known. But I actually want to, so there's several obstructions known, but I am going to focus on the simply connected case, and I want to talk about where we actually get these examples from now. Okay, so if you want to create a Riemannian manifold of non-negative sectional curvature, there are 4 starting points, 4 spaces that we just know have these kinds of metrics, and then 2 ways of combining these spaces. 2 of the main building blocks are actually quite well known. So compact Lie groups with their biinvariant metric, you just do the calculation and they all admit metrics of non-negative sectional curvature. You can express the curvature in terms of the length of the Lie bracket of vector fields. And so sorry, the length squared, but nonetheless, like you get these metrics, and then the other sort of main of the 4, these 2 are definitely the 2 most important ones, is a result of Grove-Ziller that says if I have a cohomogeneity 1 manifold and I know something about the singular orbits, then I have this this kind of metric on here. So let me talk about what a cohomogeneity 1 manifold is very quickly, because it's going to be coming up quite a bit. So the terminology just means that I have a manifold upon which a group is acting, and the action of the group is required to have an orbit which is codimension 1. So if you look at all the points of the manifold, hit them with the group, you get a bunch of embedded submanifolds. If one of those things has codimension 1, you call the action a cohomogeneity 1 action. And it turns out there's a fundamental structural result due to Mostert, which had some errors that were patched up by Galaz-García and Zaré, which asserts that in this setting, that when you're in the setting of a cohomogeneity 1 manifold, that that the following picture actually tells you a lot of what's happening. So I'm gonna draw a picture of RP2 here. So I'm gonna use the hemisphere model. So we have RP2 here. And I'm imagining that the equator of RP2 is being identified via the antipodal map. So the equator in this picture is being identified that way. And if I look at the circle action on this space, S1 acts here, and it just acts by rotating. So you take the standard rotation action on the 2 sphere, and it descends down here. So if you pick a point that's not the North Pole and not the equator, a point right there, and you look at its orbit, you get a circle here. And not only do you get a circle, but in the context of the action I've described, the isotropy group at this point is trivial. The only point of the circle which fixes that point in RP2 is the identity. And this is the generic behavior. For any line of latitude you pick, again, apart from the North Pole and apart from the equator, you get this picture. But then you have these 2 singular orbits. So you have the singular orbit at the North Pole. Singular just means that the isotropic group is bigger than the trivial group. And in fact, the entire circle fixes this point. And then if you also look at the equator, I just hit something with my hand, I apologize. If you also look at the equator here, the Z2 inside of the circle fixes that equator pointwise. So the orbit is a circle, but the isotropic group is a little bit bigger. And so you have these non-regular orbits in this case. And this theorem of Mostert, again, patched up by Galaz-García and Zaré, asserts that if you have a cohomogeneity 1 manifold and the orbit space is an interval, you always get this kind of picture where you have the manifold's foliated by these regular orbits, and then you have these two non-regular orbits. If your manifold is simply connected, which of course RP2 is not, then you actually get singular orbits, meaning that the dimension of those two weird orbits is smaller than the dimension of the big manifold, and that's the case that Grove and Ziller study here. By the way, just to mention it, if you take a small disk bundle over this, gosh, I keep hitting the wrong thing, I apologize. If you take a small disk bundle over this singular orbit right here, you get sort of a polar ice cap. If you take a small neighborhood around the singular orbit down here, you get a Mobius band, and you can obtain RP2 by gluing those two things together. And this is sort of the first non-trivial example of what's a double disk bundle that we're going to see later. Okay, so anyway, these are the two main building blocks of closed manifolds with non-negative sectional curvature. There are two other ones I want to mention. So a result of Cheeger from 1972 asserts that if you take two compact rank 1 symmetric spaces, so these are spheres or RPNs or CPNs or HPNs or even OP2, and you connect two of them of the appropriate dimension, well, you can deform the positively curved metric on those spaces in such a way that near the boundary it's a product of an interval cross sphere of appropriate dimension, and you glue them together. And so this is another building block, but it's quite limited. For example, in odd dimensions, this construction only gives back spheres, and in even dimensions, it only gives back a very short finite list of spaces. There's one other building block known. This is a result of Rafael Torres, very, very recent. So he looked at a nonlinear quotient of S2 cross S2. So you don't just take the usual metric on S2 cross S2 and then find some quotient. It's some very strange metric on S2 cross S2 that still has non-negative sectional curvature. And then there's a nonlinear Z2 action, which is free in the quotient space. Torres shows, the action is isometric, so you get this metric on this quotient. Torres actually constructs this example by gluing disk bundles together. So again, this will be another example of a double disk bundle when we get to it. But these are the four starting points. Beyond those four starting points, there are two ways of combining them. The obvious one is you just take products of non-negatively curved things or non-negatively curved. You just do the calculation that pops out. And then the slightly more surprising one is that Riemannian quotients. So if you have a Riemannian submersion, the quotient space inherits one of these metrics from the total space. This is a result due to O'Neill. He computed formulas for how curvature changes when you go down via Riemannian submersion. And every known example of a non-negatively curved manifold is built out of these four main building blocks together with these two operations. So this is our complete list of what we know at this point. Okay, so I want to return back to maybe a conjecture here. So a conjectured obstruction, because it's going to really, again, focus our talk on exactly what I want to hone in on for again, purposes of this talk. So there's a conjecture due to Bott, which says, at least in the simply connected case, we can state it like this: a simply connected closed manifold with a non-negatively curved Riemannian metric should be rationally elliptic. Now, if you haven't heard that terminology, rationally elliptic, before, all that means, or one definition of that in this context, is if you take all the rational homotopy groups of the manifold, tensor them with the rationals, so throw away all the torsion and just look at the free part, the total dimension of all of that should be finite. And the quintessential example of rationally elliptic things are spheres and compact Lie groups, or even non-compact Lie groups. So this is somehow saying that from the perspective of homotopy groups, the topology is quite simple in some sense. Now, again, you're throwing away all the torsion information, so there's still a lot of complication that's being allowed, but somehow you're just trying to get your hands on what's happening rationally. So I just said that this is what rationally elliptic means. I want to focus attention, for purposes of this talk, on a very narrow question. And that is, which rational spheres emit metrics of non-negative sectional curvature? So when I say rational sphere, what I mean is a simply connected, closed, smooth manifold with the rational cohomology, or equivalently, the rational homotopy groups being isomorphic to that of a sphere of the same dimension. And so from the perspective of the Bott conjecture saying things should be rationally elliptic, these are in some sense the simplest spaces we can study. So if we can't answer this question, the general question, of course, is quite hopeless. Okay, so what are the examples that we know of this thing? What are known metrics of positive or non-negative sectional curvature on rational spheres? So to begin with, I want to focus on the odd dimensional case, and there's not really a great reason for splitting it into positive and non-negative sectional curvature, but I do think the result is interesting. So in the odd dimensional case, of course, if you want a positively curved odd dimensional rational sphere, the standard sphere is an obvious example. So that's, of course, in the list. Perhaps more surprising is there's two other examples. There's this homogeneous space called the Berger space. The SP1 max indicates a very weird embedding of the 1x1 quaternionic matrices satisfying the unitary condition into SP2. And then this P2 thing right here is a cohomogeneity 1 manifold. It's also a 7-dimensional manifold, just like the SP2 mod SP1 max. This cohomogeneity 1 manifold, where it gets this name from, is there's a classification of the possible cohomogeneity 1 manifolds that can admit an invariant metric of positive sectional curvature. And the answer is that the list is known examples together with potentially two infinite families in dimension 7 called the P family and the Q family. P1 and Q1 were already known to admit metrics of positive sectional curvature, and then the latest result on this is that P2 also does. For the higher P's and the higher Q's, it's currently unknown, but those are kind of the hot candidates right now for admitting these kinds of metrics. Okay, what about in even dimensions? Well, a significantly shorter list. In even dimensions, the only known example of a positively curved rational sphere of even dimension is the standard sphere. So yeah, short list. Now, of course, positive sectional curvature is quite rare, quite hard to achieve. So maybe the classes open up when you allow non-negative sectional curvature. And in the odd dimensional case, that is totally accurate. Once you allow non-negative sectional curvature, the list explodes. So this T1 S2n, that's the unit tangent bundle of the 2n sphere. So you have examples in arbitrarily high dimensions coming from those. This SU3 mod SO3, this thing is called the Wu manifold. It's a 5 manifold. And it's actually going to appear in the talk several more times. So this plays a prominent role in what's to come. And then these biquotients, G2 mod SU2, there's, if I remember correctly, 3 of them. And then these spaces down here, the B7 and M7 are some cohomogeneity 1 manifolds. The B7s are the Brieskorn variety. Sorry, I said that wrong, which include the Curvaire spheres. So they include some exotic spheres. And then the M7 is just another cohomogeneity 1 infinite family. And it has as subfamilies the P's and Q's I mentioned before. And then there's also these GKS spaces. So the GKS here stands for Goethe, Kerin, Shankar, Sebastian Goethe, Martin Kerin, Christian Shankar. So this is a very recent result where they generalize the cohomogeneity 1 setting by allowing quotients of that. And they're able to construct many, many, many 7 manifolds that admit metrics of non-negative sectional curvature, including all exotic spheres in dimension 7. So that's kind of a nice result. Okay, so how does this open up for even dimensions? The answer is it doesn't, to anyone's knowledge. So if I say I have an even dimensional rational sphere and it admits a metric of non-negative sectional curvature, as far as we know, it has to be diffeomorphic to a sphere. There's just no other known example. And so what I really want to explain is maybe a reason for why you would expect the odd dimensional case to be so full of examples while the even dimensional case seems not to be. And if you go back and look at all the obstructions that I mentioned earlier, there's nothing yet that would distinguish this even an odd dimensional case. And so I want to address that. Before I do that, I want to talk about some more details on these rational spheres emitting these metrics. So if you focus on the case of homotopy spheres, as I mentioned a second ago, the result of Goethe, Kerin, and Shankar indicates that all 7-dimensional exotic spheres have these kinds of metrics. And you might be thinking, well, yeah, they're spheres. Of course, this should work. But we now know through the work of Hitchin and Adams that in dimension 8K plus 1 and 8K plus 2, you can always find exotic spheres which don't even admit a metric of positive scalar curvature, much less non-negative sectional curvature. And so it really is quite astounding that all 7-dimensional exotic spheres have these kinds of metrics. And I should also mention that there's no other dimension known where an exotic sphere admits a metric of non-negative sectional curvature. So 7, all of them work, and 7 is the only dimension where we know any of them work. Continuing with this more detail, if we ask for the 4 constructions, which of those give us rational spheres? That has now been completely classified. So the last Shiger manifolds and Torres's example. Well, Torres's example is a quotient of S2 cross S2, so of course it's not a simply connected rational sphere. And then the Shiger manifolds it's very easy to see that they either give you back spheres or they give you things with the wrong Betti numbers to be spheres. So I really want to focus on the biquotient and cohomogeneity 1 case. So in the biquotient case, this was settled by Totaro and Kapovich-Ziller. The result is that if you have a biquotient, so a biquotient is a quotient of a compact Lie group by a two-sided action of a subgroup of G cross G. So if you have a biquotient that is a rational sphere in even dimensions, it must have been a standard sphere. So I wrote no examples. I mean here there's no non-trivial examples. So all examples are diffeomorphic to the standard sphere. And then in the cohomogeneity 1 case, this is a result of Lee Kennard and myself, there are no non-standard examples here either. So the 4 constructions are have been completely exhausted in terms of giving examples, at least in the even sphere case. Yeah, so where do you turn for more examples? I don't really know the answer to that. So, but I do want to give us maybe a conjectural way of explaining the discrepancy. And so this is going to lead us into the idea of double disk bundles. So I want to get the definition of double disk bundles up on the screen. So what is a double disk bundle? So we're going to have 2 closed submanifolds, B1, B2 of this double disk bundle. I'm going to often refer to them as sols because they play the role of in a lot of ways they play the role of the sol in the non-compact case. So I have these 2 sols, B1 and B2. We choose disk bundles over those. And when I say disk bundle, I just mean the standard Euclidean disk. So diffeomorphic to the ball. We could also call them ball bundles if you'd like. So I choose 2 disk bundles, 1 over B1, 1 over B2. And then I have this very strange condition. I want the boundaries of those disk bundles, which are sphere bundles over the B's, to be diffeomorphic. And this is a very non-trivial condition. If you just create 2 disk bundles at random, they are not going to have diffeomorphic boundaries. Once they have diffeomorphic boundaries, I can choose a diffeomorphism between those boundaries, and then I glue the 2 disk bundles together via that diffeomorphism. And of course, you obtain a closed manifold in this way. And that manifold you obtain is called a double disk bundle because it's created by gluing 2 disk bundles together. I want to mention that the rank of the disk, we're always going to assume it's 1 or bigger, and that's simply because a 0 disk, which is just a point in R0, doesn't have a boundary. So this whole process dies immediately if you take k to be 0. Okay, so where do you find these things? Well, I want to start off just by talking about the classification in the case of surfaces. It's kind of a neat little toy problem. You can do it in just a couple minutes. So what I want to get on the screen here is the classification of all surfaces that admit this kind of double disk bundle structure. So that means I want the total space of these disk bundles to be 2-dimensional, and because the fiber disks are all 1 or 2-dimensional, that means I have 3 possibilities for these disk bundles. Either my base is a single point, and then the only disk bundle over that is the trivial one, or my base is a circle, and then there are 2 D1 bundles, 2 interval bundles over a circle, namely the cylinder and the Mobius band. So these are all the possible building blocks I can use. By the way, I would like to point out that the base dimension changes from these examples. So we're not asserting that the base dimensions have to be the same. The only condition is that the boundaries of these double disk bundles are diffeomorphic. And of course, in this case, we get lucky in the sense that there's just not a whole lot you can do with the boundaries. If the boundaries are 1-dimensional manifolds, they're all given by disjoint union of circles. And so you're going to take these 3 building blocks and you're going to glue them together and ask what surfaces you get out of that. Now, first thing I should say is if you take a cylinder and you glue it to either one of these things over here, the resulting space you get is diffeomorphic to whichever one you picked here or here. So if you pick a cylinder for one of your things to glue, you might as well pick the other one to be a cylinder. Otherwise, you haven't really made anything new. And if you glue a cylinder to itself, then it's not too hard to convince yourself you're either going to get a torus or a Klein bottle, depending on how you deal with orientations when you glue. So that kind of handles the case where you pick a cylinder. The other options are you pick a disk or a Mobius band. If you pick 2 disks and glue, you get a 2-sphere. If you pick a disk and a Mobius band and glue, you get RP2. And if you get 2 Mobius bands and glue, you get a Klein bottle. So just to summarize the entire list, all the double disk bundles in dimension 2 consist of a 2-sphere, a 2-torus, a Klein bottle, and RP2. And I would like to point out that by Gauss-Bonnet, this list of spaces is precisely the list of surfaces that emit a metric of non-negative sectional curvature. So maybe this is your first hint that these ideas are related to each other, this double disk bundle stuff and curvature. That relationship, of course, gets less clear as you go in higher dimensions, but at least right now, it seems like there's something. Okay, so that's all the surfaces. I also want to do two other examples. One is if you're going to take your disk bundle to be the trivial 2-disk bundle over a circle, and I want to take 2 copies of that. The boundary of this thing is a 2 torus, and the mapping class group of a 2 torus is quite large. It's a GL2Z. So you have lots of different ways of gluing, and the point is that depending on how you glue a solid torus to itself, you can obtain a 3-sphere or S2 cross S1 or a lens space. Like there's lots of options here, and so this is just really stressing that the choice of gluing map is an important part of the data. You can't just say I'm gluing these things together. You have to be careful about which map you choose to glue them together with. And then the other example I want to get on the board is an n plus m plus 1 sphere has a standard decomposition, which is going to pop up again in the talk. So I take an m sphere and look at a trivial n plus 1 bundle over that. I do the same thing, reversing the letters, an n sphere with a trivial dm plus 1 bundle. The boundary of both of these bundles is an Sn cross Sm, and you just glue by the identity map, and that's going to give you the sphere. And this is the standard, like, what's the way I would say it? Like the standard Clifford picture. So if you imagine your Sn plus m plus 1 is given by n plus m plus 2 coordinates in Euclidean space, where some of the coordinates is some of the squares of the coordinates is 1, then this decomposition is just you take the first n plus 1 coordinates to have a total length of less than or equal to a half versus bigger than or equal to a half, and it gives you this decomposition right here. So it's a very standard decomposition, and what we're going to see eventually is that in the rational case, the rational sphere case, all the decompositions kind of look like this. So I wanted to get this one on the screen. Okay, so this is all about constructing examples of double disk bundles, but if all you ever did was construct them, that would not be terribly interesting. So I want to really focus on where do these things just appear? So you're minding your own business, doing some mathematics, and a double disk bundle jumps out at you. Where do these things come from? Well, I've already mentioned that cohomogeneity 1 manifolds have this structure. That's a result of Mostert, and again repaired by Galaz-García and Zarre. So what Mostert proved is that the quotient space is either an interval or it's a circle. When it's a circle, you can take a double disk bundle structure on the circle and pull it back to the cohomogeneity 1 manifold, and when it's an interval, that's when you have this foliation by regular pieces. The endpoints of the interval correspond to the singular guys on the end. And then Mostert's kind of big theorem in that paper is that you actually get this double disk bundle structure. This has been recently generalized by Mendez and Radetzky in the context of codimension 1 singular Riemannian foliation. So this is not actually in their it's not explicit in their paper, but they have a paper where they prove that the slice theorem holds in the way you might expect for singular Riemannian foliations, and then as a consequence of that slice theorem, if you have a codimension 1 singular Riemannian foliation, then you get this double disk bundle structure. So maybe just to explain this terminology, so a foliation is a partition of the manifold into submanifolds, and the singular Riemannian is indicating that you're allowing the dimension of the submanifolds to change from leaf to leaf, and the Riemannian is saying that the leaves are locally a constant distance apart, and you have this thing called a transnormal collection of vector. Saying the sentence wrong. Sorry, transnormal collection of vector fields on the thing. So, right. So where else do these things arise? Well, if we want to start adding curvature to the picture, in 1994, Grove and Searle proved that maximal symmetry rank actions in positive curvature have this double disk bundle structure. So what maximal symmetry rank means is you have an isometry group of your manifold. The isometry group is a Lie group, so it has some maximal torus. That maximal torus has a dimension, and that's what the maximal symmetry rank is. And what Grove and Searle showed is that in the context of simply connected, closed manifolds with positive sectional curvature, there's a bound on the rank of that torus, which is approximately half the dimension of the manifold. And then in the equality case, you get this double disk bundle structure, and they exploit that to actually get a diffeomorphism classification of which manifolds have these maximal symmetry rank actions. There's another result due to Wolfgang Spindler in his thesis, which says if you have a fixed point homogeneous action in the presence of non-negative sectional curvature, then you get this double disk bundle structure. What fixed point homogeneous means is, again, you have a group acting. This time you're going to allow the group action to have a fixed point set. So you look at a component of that fixed point set. That means that the group is going to act on the normal space to that component. And if that action, for any component, if that action is transitive on the sphere in the normal space, you call this fixed point homogeneous. And then what Spindler actually shows is that this fixed point component forms one of the soles and the cut locus relative to that fixed point component forms the other sol. I guess this nice double disk bundle structure. A few other results I just want to get through relatively quickly. So if I'm looking at some manifolds of a manifold that have a regular focal locus, so all the focal points have the same multiplicity, Hebda proves that in that situation you get a double disk structure where one sol is a submanifold and the other one's the focal locus. And then result of Meunier says if you're studying isoparametric submanifolds of a sphere, then those are the total space of sphere bundles. And if you fill those into disk bundles, that gives you a double disk bundle decomposition of the sphere. So these things do arise in nature quite a bit in the presence of curvature, not in the presence of curvature. They're quite geometric. And it's a bit surprising to me how little they've been studied kind of in the more abstract setting. Okay, so I want to talk next about where I hope that we can find even more examples of double disk bundles. So there's this thing called the double sol conjecture, which is basically trying to answer the question of what should the sol theorem look like in the closed setting. So it says if I have a closed Riemannian manifold with non-negative sectional curvature, then it should be a double disk bundle. So in some sense, you can rephrase Cheeger and Gromall's sol theorem as in the non-compact case, you have not a double disk bundle, but a single disk bundle. There's a little bit of an issue there with the boundary, but nonetheless, sort of the spirit of that is that this double sol conjecture, the analog of that is true in the non-compact case. And in fact, that is, in some sense, like the biggest evidence for why you might believe this. Of course, that's not the best evidence, so I want to talk about some other evidence. So there's a result of Cheeger, which says that if your manifold has a totally geodesic hypersurface, then that totally geodesic hypersurface is the boundary of one of these double disk bundle decompositions. And so that's maybe a place you might hope to look for it naturally. And then among the examples we have, the four constructions we have, as I mentioned, cohomogeneity one manifolds automatically have the structure due to Mostart, Galaz-García, and Zaré, and their quotients also do. Just you compute and it all works out. Cheeger's examples of connect summing rank 1 symmetric spaces. If you delete a point from a projective space, for example, what's left is actually the tautological disk bundle over. How do I want to say this? So if you start with CPN and delete a point, you get the tautological bundle over CPN minus 1. And the similar thing happens for the other examples. So the Cheeger manifolds are actually, looking at it in a slightly different perspective, gluing two disk bundles together. And in Torres's new example, he explicitly constructs by taking two disk bundles and gluing them together. So at least among the examples we have, the three of the four building blocks that we have, this double sol conjecture is definitely true. Yeah. So what about hurdles? Well, why haven't we proven this theorem yet? Well, there's this fourth class of spaces, Lie groups, and their quotients, which are homogeneous spaces and biquotients. The double sol conjecture is not known for this particular class of the examples. And in fact, it's even worse than that. There are Lie groups, namely the exceptional Lie groups E7 and E8, where we just don't know the answer. We don't know if they have a double disk bundle decomposition or not. Part of the issue is that these are large dimensional manifolds, and so we can construct all sorts of double disk bundles that have the right topology, but how do you recognize that it's one of these manifolds at the end of the day? I mean, that's one major issue with understanding it here. And it's known that none of the obvious processes will work. So, for example, E7 and E8 are not cohomogeneity 1 for any action by subgroups. That's a result of Kohlroas. And so kind of the obvious ways of putting this double disk bundle structure on it are not going to work. Another major hurdle, and in my opinion, this is the biggest one, is it's not known what the geometrical significance of the sols should be. So in the sol theorem of Cheeger and Gromall, the one for non-compact manifolds, the theorem, what we know about the sol is that it's totally convex. Very, very, very strong geometric property. And that gives you maybe something to look for in the double sol conjecture case. You're looking for a totally geodesic, totally convex, something like that. But the issue with that is you're not always guaranteed to have totally geodesic things. So kind of a standard example here is you take any known example with positive curvature, which is not a symmetric space, not a compact rank 1 symmetric space. So the smallest dimensional one is this homogeneous example that's called the flag manifold, SU3 mod T2. So it's positively, it has a metric of positive sectional curvature, and you just kind of perturb that metric a little bit. It still has positive sectional curvature, so in particular non-negative, but you can get rid of all of the totally geodesic submanifolds except for points and geodesics. And that means that if you require your sols to be totally geodesic, you have to be able to build SU3 mod T2 using disk bundles over points and circles. And there just aren't a lot of disk bundles over points and circles, and it's a very simple topology calculation to show that there's just no way to build SU3 mod T2 out of those kinds of building blocks. So whatever the geometrical significance of a sol is going to be, in the general case, it's not, you cannot ask for it to be totally geodesic. That's asking too much. This space does admit a double disk bundle decomposition, and if you take the standard metric, the pieces are totally geodesic. It's just, in general, we have no reason to expect that'll continue to happen. Okay, so suppose you prove the double sol conjecture. What does that gain you? So I want to go through a list of theorems by several people that will tell you what you get if you prove the double sol conjecture. All the theorems I'm going to mention are actually more like topology theorems, but the geometrical applications, again, come from the double sol conjecture. So the first result I would like to mention is in dimension 4. If we focus on the simply connected case, the complete diffeomorphism classification of the double disk bundles is that you have to get S4, CP2, S2 cross S2, or CP2 connect some with itself with some orientation. This is precisely the list of known examples in dimension 4, which admits a metric of non-sectional curvature. So if you prove the double sol conjecture in dimension 4, what you have then proven is that our known list is complete. So that's what you get in dimension 4. What is the analog in dimension 5? Well, this is a result due to Fernando, Galaz-García, Martin, Kerin, and myself. So we did the analogous thing in dimension 5, and the result there is that you get S5, you get that Wu manifold I said would come up again, and it's going to continue to come up. And you also either get S3 cross S2, or this notation S3 X tilde S2 is indicating there's a unique non-trivial S3 bundle over S2, and the total space of that is what I mean by this. Again, this is the complete list of known examples in dimension 5 that have metrics of non-sectional curvature. So if you prove the double sol conjecture in dimension 5, we now know that our known list is the complete list. Some nice closure there. You might also ask what happens in dimension 6. And there the answer is that we have some partial results, but not a full classification. So we're going to make this extra topological assumption that the second rational Betti number is 0. And then the conclusion is that the diffeomorphism classification is a 6-sphere or S3 cross S3. And again, this is precisely the list of known examples. So there's definitely seems to be some kind of connection between these double disk bundles and non-sectional curvature, at least in low dimensions. Just very briefly, I want to mention there's a fun little corollary of this. So if you prove the double sol conjecture in dimension 6, then as an immediate corollary, either the Hopf conjecture has to be true in dimension 6, or you can put a metric of positive sectional curvature on S3 cross S3. So the Hopf conjecture asserts that in even dimensions, a positively curved thing should have positive Euler characteristic. And if you think about what that means for a 6 manifold, a simply connected 6 manifold, the only way it can have positive, the only way it cannot have positive Euler characteristic is if the third Betti number is non-trivial. And then what Galaz-García, Kerin, and myself actually proved is if the third Betti number is non-trivial and you have a double disk bundle structure, then the manifold is S3 cross S3. So yeah, you have this nice result that if the Hopf conjecture is not true, you can find a counterexample on a very, very, very specific manifold. Just a nice little cute application. Okay, so what I really want to talk about in terms of theorems today is more recent result. So I'm going to call it, for purposes of this talk, the rational spheres theorem. And it's going to go back and try to address what's different about the even case versus the odd case. And so I'm just going to go through the theorem real quick. So I have an even dimensional M2N, even dimensional closed simply connected smooth manifold that's a rational sphere. And we're going to make this assumption, just for purposes of the talk, that 2N is relatively large. It's at least 8. Then, being a linear double disk bundle is the same as saying M is homeomorphic to a sphere. So what do I mean by linear? I mean that the disk bundle is actually a disk bundle inside of a vector bundle. This allows me to use characteristic classes in the argument. That's the main thing that matters with linear. And then I should also mention in low dimensions, we can change homeomorphic to diffeomorphic due to the work of Radesky and Gay, as well as the work of Galaz-García, Kerin, and myself. So we can actually improve the theorem there. But starting in dimension 8 and up, so Smale has proven that any exotic sphere in high enough dimension you can obtain by gluing two disks together. And so there's no hope of getting a theorem that has diffeomorphic for any dimension above 5 that has exotic spheres in it. And so in dimension 6, we just kind of get lucky. There are no exotic spheres. So that's why we get diffeomorphic from there. Okay, so this theorem has an assumption of a very strong assumption about the rational topology. But what's interesting to me is that you get a very strong integral topology conclusion on it just from the structure of a double disk bundle. And this is very, very, very false in the odd dimensional case. So this is maybe a theorem which shows a fundamental difference between the even case and the odd case. And then again, in light of the double soul conjecture, that the list I showed you in that chart is complete except for allowing homotopy spheres. So that would maybe explain what's going on there. Okay, so how do you prove such a theorem? How do you know that this rational spheres theorem is true? So the setup here is I'm going to have two souls, two submanifolds, where my manifold is given as a union of disk bundles over those souls. And I'm going to call L the boundary of one of these disk bundles. As a reminder, the disk bundles are diffeomorphic. The boundaries are diffeomorphic, so L is just either one. It doesn't matter. L has an inclusion map into the big manifold, and the projection from L to each of the souls is a sphere bundle. And in some sense, the main idea of the proof is, well, L has two different sphere bundle structures, and you play them off of each other and keep learning more and more and more about the topology. But the immediate goal is we're going to compute the integral cohomology of the pieces and use Meyer-Vietoris. And what we'll find is that M has the integral cohomology groups of a sphere, and then the Poincare conjecture gives us the homeomorphism classification. So that's the outline, but of course, how do you achieve that? Well, the very first step is we're going to try to get some rational control. So we know a whole lot about the manifold M rationally. It's a rational sphere, and we want to turn that into information about the rational cohomology of L and the two souls. So you have this inclusion map that I mentioned before. It has a homotopy fiber, so you can convert any map into a fibration. So you do so, and you get this homotopy fiber F. And generally speaking, excuse me, I find this homotopy fiber very hard to understand, but we get lucky. Grove and Halperin studied this thing in 1982, and the rational homotopy type is known. So it turns out that it's completely determined by the codimensions of the souls, orientability of the souls, and then, sorry, it's not completely determined. It's determined up to 2 or 3 options by that data I just specified, by the codimensions of the souls and by the orientability of the souls. And so that means we understand the topology not just of M, but also of F. And then if you understand something about maps in exact sequences, now you can learn a lot about L. And luckily, Galaz-García, Kerin, and myself, as well as Lee Kennard and myself, have put quite a bit of effort into studying the connecting homomorphism and the long exact sequence of rational homotopy groups you get from this vibration. And the result is that we understand the map, at least from pi odd to pi even. And in the case of M being a rational sphere, pi odd is one-dimensional, which means we, in some sense, completely understand this map, at least on the odd-dimensional case. And the upshot is if you play all this against each other, rationally, meaning in the sense of rational cohomology, L and the two souls have to look like the standard decomposition of a sphere that I mentioned several slides ago. So what I mean by this look like is from the perspective of rational cohomology, B1 looks like an SL1, B2 looks like an SL2, and L looks like the product of the boundaries of that, which would be an SL1 cross SL2. And again, this is all rational. Great. Now, of course, it's not surprising that with a strong assumption on the rational type of M, we can get strong conclusions about the rational type of the pieces. But it is kind of interesting to see this structure pop out kind of right off the bat. So how do you get integral control out of this? So this is rational control. How do we bump this up to integral control? Well, one observation I want to make right from here is that the dimension of the parity of L1 and L2 have to be different. If they're the same parity, well, then this space here would have odd dimensions, so there's no way it's going to be part of a two-dimensional sphere. So the L1 and L2 have different parities, and that in particular means that they're different numbers. And so we're going to go ahead and say, so the L1 and L2 control the ranks of the disk bundles, and therefore control the dimensions of the souls. And so we're just going to reorder things so that B1 has smaller dimension. And then there's a nice little argument here that's going to give us integral control over the cohomology of B1. the smaller dimensional thing, as well as L. And the idea here is we're going to use the Leray-Hirsch theorem and play these two sphere bundles against each other. So we have a sphere bundle for B1. It looks like an SL1 goes to L, goes to B1. And because B1 is small dimensional, the spectral sequence for this is a tall, narrow thing. So like the cohomology of B1 will be concentrated in a small thing, and then this cohomology group coming from that fiber will be something really high up here. And then as a just immediate application, all differentials are trivial. There's just nothing to hit. The only differential you have vertically is this, or the only non-trivial cohomology group you have vertically is this one. And so all the differentials just end up being trivial. So here's the main point of this in terms of Leray-Hirsch. If I have some torsion in the cohomology ring, say there's torsion right there in the cohomology ring of B1, then that torsion, of course, survives into the torsion of L. And not only that, but Leray-Hirsch is going to tell us if you take the cohomology class that projects to this thing and cup it with the cohomology class you get there, then that cup product is non-zero. That's what Leray-Hirsch is going to tell you. So you get cup products between torsion elements and this free thing being non-zero. And now we're going to turn the bundle around. We're going to look at the other one. SL2 goes to L, goes to B2. Because B2 has larger dimension, practically speaking, this one ends up being a long but short kind of a thing. And so now you could have potentially interesting differentials. But the way we're going to use this is, it turns out if you look at where the smallest torsion is, the smallest torsion misses all the differentials. So the smallest differential that actually hits down there in the base will miss the torsion there. And so here's how we're going to get a contradiction. If you take the Z all the way up here and cup it with the torsion down there, and there has to be torsion there in order to give L the right cohomology. If you cup those together, of course you're going to get zero, because that lies in the cohomology of B2, but it lands outside of it out here. But then when you pull that back to L, you can prove that pullback map is injective. And so on the one hand, from this picture, in L, the cup product of small torsion with this high Z is non-trivial, and then down in here, if you run that same argument, it is trivial. And the only way out of that contradiction is if there's just no torsion in B1 to begin with. So that's the idea behind the argument for how you get B1 to be torsion-free. Once you start getting things torsion-free, you kind of get a domino effect, but it stops relatively quickly. So you have the sphere bundle L to B1, and so once you know that that B1 is torsion-free, it's pretty quick to show that L is also torsion-free. Yeah, and so that's going to lead us to the next bullet point here. So now we're going to do a quick spectral sequence argument on the other vibration. And the big deal I want to pull out of that is just that you learn this fact, that the L1 plus 1 has to divide L2 plus 1. Where that's happening in the spectral sequence argument is, again, you have the cohomology of B2. It's kind of copied right there. And if you have torsion in the cohomology of B2, you look at the largest torsion up there. And then in terms of the filtration you get at the end of the day, that diagonal is what contributes to the topology. It's supposed to be torsion-free because we now know that the cohomology of L is torsion-free, and that tells you where this has to be placed relative to that thing, and that gives you this divisibility criterion. Okay, so let me kind of summarize where we're at. Oh, sorry, I didn't say this. That divisibility criterion implies that the L1 is the even and L2 is odd, because if you flip it, you would have an even dividing an odd, which is impossible. So here's our setup. We have a sphere bundle over the larger of the two sols. We know L1 is even, we know L2 is odd. We have this divisibility thing, and we know the cohomology of L. And the obvious question is, does this information force B2 to be a homotopy sphere? I spent a long time trying to prove the answer to this is yes, but it's not. No, there's actually a very easy counterexample. It's our friend the Wu manifold from before. So this manifold, it's a 5 manifold, and it's defined as a homogeneous space, and if you just kind of take the obvious SO2 inside of SO3, you get this homogeneous fibration. It turns out the fiber is a 2-sphere, and then the total space had cohomology computed by Olaf and Wallach a while ago, and the result is that it has cohomology like up in here. So this was quite surprising to me that I really assumed that we would get a homotopy sphere out of this, and you just don't. So you get this counterexample. So that was kind of the first surprise of the story. By the way, this doesn't ruin the rational spheres theorem, because the L you get It's also a bundle over S2 with fiber S5, and so you know lots of homotopy groups from that. And then homotopy groups with a Riemann manifold are also known, and that's enough to conclude there's no L which simultaneously fits there and as a bundle over S2 with fiber S5. So this doesn't ruin the rational spheres theorem because we know enough homotopy groups, but of course that can't work in higher dimensions. So here's kind of the big theorem that finished everything off. In that setup that we were just talking about, you can get a homotopy sphere, you can get the Wu manifold with a two-sphere over it, but that's it. So somehow this one counterexample is the only counterexample. And the rest of the paper is devoted towards proving this theorem. Once you get this, it's pretty easy. I see that I'm basically out of time, so I'll just go through this very, very briefly. This is actually like the last bit of the slide. So the main idea is you have so many spectral sequences and whatnot that you're able to determine both the integral and the Z2 cohomology of B2, assuming it has torsion in its cohomology ring. And then you actually use the Steenrod squares to deduce that you have control over L2 and L1. They're related by this. And since you know everything about the topology, you can go ahead and work out that if the base is 5-dimensional, you get the Wu manifold, and that other sphere had to be a rank 2 sphere. From here on out, we can assume that L2 is bigger than 4, and this is kind of the big deal. That means that the bundle is spin, and so the classifying map actually, the classifying map of this vector bundle that gives you the sphere bundle actually lifts to B spin, and that lifting map is understood in the context of cohomology with Z2 coefficients. And so the conclusion is that the Stiefel-Whitney classes of this bundle have to vanish, which tells you the Euler class vanishes, and now that means that the cohomology of B2 has to inject into the cohomology of L, which is torsion-free, and so B2 is also torsion-free. So I'm sorry I rushed there at the end, but yeah, that's the main heart of it. So thank you for your attention. I'd love to entertain any questions you guys have.